Hello everyone, this is Recitation at Lehigh University. Today we're taking a look at a cavitation problem for CE 222 Fundamentals of Hydraulic Engineering. The problem today is on cavitation. So let's start with the problem statement. A pump is installed in a 200-meter pipeline. So let's start with the given. The total length is 100 meters. To lift water at 20 degrees centigrade, so the temperature is 20 degrees centigrade from reservoir A to reservoir B. So instead of picking any point, let's pick a point at the surface, call that A, and pick a point in the upper reservoir, call it B. So we'll want the water going in this direction. The pipe is rough concrete with a diameter of 80 centimeters. So diameter is 80 centimeters, so that's 0.8 meters. The design discharge is 5 cubic meter per second. So we want a discharge of 5 cubic meter per second. Determine the maximum distance from reservoir A that the pump could be installed without encountering cavitation problem. So this length here from the reservoir leading up to the pump. So let's pick another point here just before the pump, call it P. The choice of this point actually makes the problem simpler, because if you were to put or pick a point on the downstream side of pump, then the pump head also comes into play. So if we pick a point before the pump, since it's a cavitation problem, this makes it a simpler setup. So we want to find out this length of the pipe just before cavitation starts becoming a problem. So this is to find. We know the pipe is rough concrete. So the couple of things we can add here. The roughness is 0.6 millimeters or 0.0006 meters. When cavitation occurs, the pressure of the liquid just reaches its vapor pressure, meaning at that pressure the phase of water in this case will go from liquid to gas. So let's add the vapor pressure of water at 20 degrees centigrade, 2.37 into 10 to the power 3 Newton per meter squared. And also let's add a specific weight of water, 9790 Newton per meter squared. Okay. First thing, we know the material, so we know the roughness, we know the diameter. We can get the relative roughness of this pipe. 0.0006 meters divided by 0.8 meters. And that will be 0.00075, and that is unitless. The viscosity, let's add that here as well at 20 degrees centigrade. Viscosity is 1 into 10 to the power minus 6 meters squared per second. The other thing we'll need to find out the friction factor is the Reynolds number. For that we'll need velocity. Velocity equals the discharge divided by cross-sectional area of the pipe. Q is 5 meter cube per second. Area is going to be pi over 4 diameter squared, and in this case diameter is 0.8 meters. Let's just use that. And that'll give you a velocity of 9.95 meter per second. Using Moody diagram, then we can find the friction factor. Actually, let's do Reynolds number here first. Reynolds number equals V times D, so velocity times diameter divided by the kinematic viscosity. We have velocity, just calculated, 9.95 meter per second times diameter 0.8 meters divided by 1 into 10 to the power minus 6 meters squared per second. Using the relative roughness value here and the Reynolds number, which comes out to 7.96 into 10 to the power 6, we can then find friction factor from Moody diagram. In this case, it's going to be 0.0185. So here, a couple of quantities will be useful later, so I'll just add this to this corner. The velocity of 9.95 meter per second, the friction factor 0.0185. This will be useful when we actually do the calculation. Start with the energy equation. If you use energy equation from point A to point B, we get PA over gamma plus ZA plus VA squared over 2Z equals pressure head at point P plus elevation head at point P plus velocity head at point P plus the head loss going from point A to point P. we can simplify this expression. So at point A, it's exposed to the atmosphere. So this one here is going to be P atmospheric. So this part right here. If we pick this one, the center of the pipe as the datum, this one then becomes the water height above the pipe, which is 4 meters. The velocity for a large reservoir can take that to be 0. The pressure at point P, since we're dealing with just cavitation occurring, or just before cavitation occurs, we'll use this critical pressure here as the pressure at point P, 2.37 into 10 to the power 3. So that's Newton per meter squared. Gp goes to 0. Then we can calculate the velocity head using the velocity that we earlier found out, and we can expand that into minor and major head loss components. So we can express that as P atmospheric over gamma plus 4 meters equals P at point P, the pressure at point P, which is your vapor pressure. So I'll just go back to the notation for now, over gamma plus velocity head in the pipe plus head loss going from A to P. You can bring the head loss on your left hand side, everything else on the right hand side. Head loss going from point A to point P equals, you can combine these two. So P atmospheric, so I didn't write it down. So P atmospheric is 1.014 into 10 to the power 5. Let's take the units outside. So PV is 2.37 into 10 to the power 3. It's Newton per meter squared over gamma. Gamma is 9790 Newton per meter cube. Velocity head 9.95 meter per second, so that's the velocity. Velocity squared over 2 times gravity, 9.81 meter per second squared. Then the head loss, let's see what else. And we need to subtract ZA, which is 4 meters. It stays positive. Okay. Then, so this term so everything is known here, everything is known here. So you can calculate the total on the right hand side, 9.064 meters. So that's your head loss going from point A to point P. And let's add that value in this corner here. .064 meters. Let's take a look at the head loss term on the left hand side. Head loss going from point A to point P can be expressed as the sum of the minor and major head losses. Summation K for the minor head loss summation, minor head loss coefficient summation, plus F L over D V squared over 2Z. And in this case, we use V, might have used VP at some point, but that's the only velocity we need to worry about in this problem. So here we know the velocity. The length L is the unknown. That's the part we're trying to find out. F we already determined in the beginning. We know the diameter, and in this case the loss at the entrance is the only source of minor loss, so this here is just going to be equal to 0.5. So 0.5 plus F is 0.0185 times the unknown length L divided by the diameter 0.8 times velocity squared times 9.95 meter per second squared over 2 times acceleration due to gravity and you can simplify this to give you 2.53523 meter plus this part 0.1167 times the unknown length L. So just remember the unit M is embedded within L. So with this we have an expression for the left hand side. Now we can go back to step 2 and plug this on the left hand side. So we'll have finally the fourth step 2.523 meter plus 0.1167 liters times length L equals 9.064 meters. You can then solve for the unknown length L. .064 meters minus 2.523 meter divided by 0.1167. You can calculate that to get 56.1 meters. So we want to be just a little conservative, so you can always use some kind of factor. In this case, we're just trying to be critical, so we'll just live with the rounded down value here. So L of 56 meter is the maximum length of pipe that we can use. before cavitation starts becoming a problem. And I'll see you guys in the next video.